those questions when you have time, right?
Yes.
All right. Okay. Now on the screen you can see infrared spectroscopy. So this is our today's topic, right? First of all, I'm going to show you a PowerPoint presentation. After that, I'll show you some other slides, and then we are going to do a few questions related to it, right?
Yes.
All right, fine. Because the feedback which was taken from you people, you were of the opinion that we should do some practice questions during the class. So that's why I have started inculcating the questions as well, right? Okay.
Yes.
So now I'll start this infrared spectroscopy. The content we are going to cover is prior knowledge, origins of infrared spectra, vibration of bonds in a molecule, the infrared spectrophotometer, uses of infrared, interpretation of infrared spectra, characteristic absorption frequencies, and checklist, right? So let's start. Before we start, we should know about the bonds. Different covalent bonds have different strengths due to their masses of different atoms at either end of the bond. If you have methane or oxygen, or if you have ethanol, not oxygen, ethanol, methane, or alkyl halides, that is called as halogenoalkane, you know that there are different covalent bonds and they have different strength. Actually, strength depends on the masses of the different atoms attached to the central atom. So every molecule has a different strength, right?
Yes.
So as a result, the bonds vibrate at different frequencies. So when the strength of the bond is different, so that means that the bonds they are going to vibrate at different frequencies. The frequency of the vibration can be found by detecting when the molecule absorbs electromagnetic radiation. So if we want to know about the frequency at which the molecules vibrate, what we can do, we need to know which type of electromagnetic radiations are being absorbed by the molecules. All right. So various types of vibrations are possible. Now I'm going to show you the vibrations. Actually, have a look here. You can see symmetric stretching. And if you look at the arrows, this is water. I'm showing all the types of stretching and bending in water so you'll get a very clear idea. In the first picture where I have written symmetric stretching, you can see that both the bonds they stretch downwards and both the arrows they are of equal magnitude. So that means that the stretching is symmetrical. That means both are stretching down. Is it clear, Anika?
Yes.
Good. Now comes the bending. I'm going to show you the animation so you'll get a very clear idea. Just let me explain this. After that, I'll show you the animation. Then the bending. Bending means that they are going to bend like this, downwards or upwards, downwards or upward. I'll show you. Just a minute. Yeah. Okay. And then the asymmetric stretching. Can you see that there is one arrow which is going in upward direction, the last picture, and there is an arrow which is going in the downward direction. So that means one is stretching down and the other is stretching up. Yeah. So this is called as, so the first and the last diagram is about the stretching. The first one is symmetric stretching. I'll show you soon. And the last one is asymmetric stretching. And as far as the diagram in the middle is concerned, it's about the bending. Now have a look. So this is symmetric stretching. Can you see that both the bonds, they are stretching down? So this is called as symmetric stretching. The red ball is actually the oxygen and the white balls are the hydrogen. And this is the picture of or the diagram of the water molecule. Is it clear? Symmetric stretching is clear?
Yes.
Good. Now comes the asymmetric stretching. Now it's very clear that they both are not symmetrical. One is stretching down, the other one is stretching up. So this is called as unsymmetrical stretching or asymmetric stretching. Yeah. Now the last one, bending. Now you can easily see the bending, which I was talking about. I showed you in the previous slide, the middle diagram, this one. Oh, sorry. This one. This one in the middle. So this was about bending. So again, symmetric stretching,
Yes.
then asymmetric stretching, then bending. All are clear?
Yes.
Good. Now, this is the spectrophotometer. In your syllabus, the diagram is not in your syllabus, but I just wanted to show you that you will get an idea that how infrared spectroscopy works. So if you look at the picture towards the very left side is the source of electromagnetic radiation. And which type of radiation would be used? Infrared radiation. All right. Now you can see two rectangles. The bottom one is the sample tube and the upper one is the reference beam. So we are going to do two types of beams. The incident beam, which is going to pass through the sample under observation, and the upper beam, the reference beam, is going to pass through the reference solution. Now,
Okay.
after passing through the solution, the beam would be transmitted, all right? And then it would pass through the monochromator, which is going to select the light of one color, and then photometer, and then the recorder, which is going to record the infrared radiation. Now, I'm going to just read out what is written underneath it, so it'll make sense to you. A beam of infrared radiation is passed through the sample. You can see an incident beam. I'm using a cursor to show you because I'm showing this on the laptop, right? So as I'm now working on the iPad, so I have to use this cursor. So a beam of infrared radiation is passed through the sample, and then a similar beam is passed through the reference cell. So the rectangular box, gray rectangular box, is the reference cell. The frequency of radiation is varied. The bonds vibrating with a similar frequency absorbs the radiation. The amount of radiation absorbed by the sample is going to be compared with the reference. The results are collected, stored, and then plotted to get a mass spectrum. Is it all clear?
Yeah.
Any question, Bita?
No.
All right. So have a look here. Now, the first diagram, a bond will absorb radiation of frequency similar to its vibration. All right. So this is the normal vibration. Now, after absorbing the energy, it'll start vibrating faster. Right? All right. So identification of particular bonds in a molecule. Now, this is very important. The presence of bonds such as OH and C double bond O within a molecule can be confirmed because they have a characteristic peaks in identifiable parts of the spectrum. Now, what he's trying to tell you, that is the presence of the bonds, they're like OH bond and C double bond O. As the atoms which are connected through a covalent bond, they are different. In the first one, OH, the covalent bond is formed between oxygen and hydrogen, and they have different atomic masses. And then C double bond O, the second covalent bond is between carbon and oxygen. So you can also see that the first is OH, that is a single bond, and C double bond O is a double bond. So which two strings are different? Number one, the type of a covalent bond is different. Number two, the atoms which are involved in making the covalent bond, they are also different, right? So
Yeah.
if they are different, their atomic masses would be different. If their atomic masses would be different, they are going to vibrate at a different frequency. If they would vibrate at a different frequency, they are going to absorb the infrared radiations of different frequency. Does it make sense?
Yes.
Great. Identification of compounds by direct comparison of spectra. The only way to completely identify a compound using IR is to compare its spectrum with a known sample. The part of the spectrum known as the fingerprinting region is unique to each compound. Now, what is a fingerprint region? I'm going to tell you. Actually, you know what? If you remember when we were doing the mass spectrum and I made the spectrum and I drew the peaks, they were in upward direction. Do you remember that? I drew
Yep.
the line to up in upward direction. But when we are going to see the infrared spectrum, you will see that the peaks are in downward direction. So when they are in downward direction, if you put your hands in downward direction, the fingers they are pointing downwards. Yeah, same is
Okay.
the case with the spectra. All right.
Okay.
So the peaks would be in downward direction, and when you put your hand down, then the fingers would be pointing towards the ground. So same is the case with the infrared spectrum, that the peaks would be towards the bottom. Yeah.
Okay.
All right. So infrared spectra are complex due to many different vibrations taking place in each molecule. Total characterization of a substance based only on its IR spectrum is almost impossible unless one has computerized data handling facilities for comparison of the obtained spectrum with one in memory. Actually, what we do, we connect the data. We connect the data system with the spectrophotometer. So when the bonds, the different covalent bonds, they will absorb different type of infrared radiation, and they are going to vibrate at different frequency. That frequency is read by the spectrophotometer, and then that frequency goes to the that system data, and it is going to be analyzed. Oh, this frequency matches with C double bond. Oh, okay, fine, this is C double bond. Oh, this frequency matches with OH bond, so this is OH bond frequency. So in this way we interpret different types of peaks, right, Anika?
Yes.
The technique is useful when used in conjunction with other methods like NMR, nuclear magnetic resonance spectroscopy, and mass spectroscopy. Although this technique, the analytical technique to know about the compounds, that is IR spectrophotometry, this is very important, but you are unable to identify the whole compound only by using IR. No, you have to use some other techniques like nuclear magnetic resonance, which is called as NMR, or you have to take the help of MS, which is called as mass spectroscopy, right? So when we are going to use three, four techniques with each other, then we will be able to identify the whole compound. Does it make sense?
Yes.
All right. Now, peak. When I'm going to show you the peaks. Peak position depends on the strength of the bond and the masses of the atoms joined by the bond. We have already talked about it, right? Because you know why peak would be formed? Actually, the peak is going to be dependent on the infrared radiations would be absorbed. This infrared radiation would be again dependent on the type of frequency on which the bonds are vibrating. Yeah.
Okay.
So strong bond. I hope everything is making a very clear sense to you, Anika.
Yeah.
All right. So strong bonds and light atoms, they absorb at lower wave number, and weak bonds and heavy atoms. When I say heavy atoms, that means of greater atomic mass. Weak bonds and heavy atoms, they absorb at high wave number. This is a particular or typical type of infrared spectra. Now, can you see these peaks which in the downward direction, just like our fingers?
Yes.
Yeah, so this is the infrared spectrum. Now, if you check the extreme right, left side, that is the y-axis absorbance is given. Towards the towards the left side, absorbance is given. Towards the right side, y-axis transmittance is given, and then frequency has been taken here on the x-axis, and opposite to it we have wavelength. Yeah, and then these are the different peaks. Now, these peaks are characteristics. These peaks are characteristic of a compound. Now, the peaks are going to be made according to the covalent bonds which are present in the compound, right? So, vertical axis absorbance, horizontal axis frequency and wavelength. The stronger the absorbance, the larger the peak. Now, if the infrared radiations would be absorbed strongly, then we are going to get a larger peak. And then frequency and wavelength, they are on the horizontal axis. Now, there you go. This is called as the fingerprint region, the blue one. Yeah.
Yeah.
Organic molecules have a lot of CC and CH bonds within their structure. Spectra obtained will have peak in the 1400 per centimeter per centimeter to 800 per centimeter range. This is referred to as the fingerprint region. The pattern obtained is characteristic of a particular compound. The frequency of any absorption is also affected by joining atoms or groups. So towards this side, we are going to get the fingerprint region. Now, after that, if you check this, you get a very clear long peak between around 1750. Can you see this, Anika?
Yes.
Yeah. So this peak, after 1600 comes 1700, and after 1718. So this is a very long peak. That means this is a very strong signal. And let me tell you that the peak which is made at around 1750 is for the carbonyl group, that is C double bond O. Is it all clear?
Yes.
All right, good. The now here it is. Now they have mentioned it. I have highlighted this, that the green belt where this green or aqua belt has been made, that is around 1750. The carbonyl compound shows a sharp, strong absorption. It's written underneath. I'm reading it from there. Strong absorption 1700 and 1760 per centimeter. This is due to the presence of carbonyl bond, that is C double bond O. Is it clear?
Yes.
So this is the IR spectrum of what? Of a carbonyl compound. Now the next IR spectrum of an alcohol. Now I am simply going back to this slide. I am simply highlighting the peak which is important to identify the compound. So if you want to identify carbonyl compound, you simply need to look for the peak around 1700 per centimeter to 1760 per centimeter. If you are getting a very sharp and long peak in this range, then it is confirmed that a carbonyl group is present in the compound. Yeah.
Okay.
All right. Now the next slide, which I was showing you, if you get a peak between, just check the x-axis, if you get a peak between 33,000 or 3200 and 3600, this range, yellow part, yellow belt,
Mm-hmm.
then this is a particular absorption peak for, particularly for OH group. So if a compound has an OH group in it, that means an alcohol is present, and you are going to get a broad, long and broad peak at the frequency which is between 3000 to 3600. Is it clear? This is due
Yeah.
to the presence of OH bond. Yeah, I'm repeating again. This is for carbonyl and this is for alcohol. So this is
Okay.
for actually aldehyde and ketone, and this is for alcohol. All right. Now, what happens if there is a carboxylic group? I hope that you remember that carboxylic acid is C double bond OOH. Yeah.
Yeah.
So that means in carboxyl group, actually the name carboxyl is a combination of two groups, that is carbonyl plus hydroxyl. So when you are going to add carbonyl and hydroxyl group, then you get carboxyl group. So that means that in carboxylic acid, you are going to get two peaks. One peak that is at 1760 or 50, that is for C double bond O. And on the same spectrum, we are going to get a peak at 3200 per centimeter, which shows the presence of OH, because carboxylic acid is going to have carbonyl group and alcoholic group. So we are going to get two distinctive peaks in the in the infrared spectrum. Is it clear?
Yes.
Good. So have a look here. By the way, this is a long and a long pointed sharp peak, and this is a, a broad peak. So you should know about it. This would not be sharp; it would be broad. Now have a look. Now check what's the heading of this spectrum? Infrared spectrum of a carboxylic acid. I hope that you can easily see that there are two types of peaks which are present. One is the carbonyl peak, and the second one is carboxyl group. So carboxylic acids show a broad absorption between 3200 and 3600 per centimeter. This is due to the presence of the OH bond. They also show a strong absorption around 1700 per centimeter. This is due to the presence of C double bond O. Is it clear?
So it's the same as the alcohol, just with the additional one, just the
Yeah.
additional.
Yes, you are going to get the alcoholic peak as well as carbonyl peak. Why? Because in carboxylic acid, both the groups are present. And in
Okay.
carboxyl, we have CO, the double bond O, OH. Yeah. So that means I'll try to write if possible. C double bond O and OH. Yeah, can you see this? What I'm doing it with the pencil? Yeah. Can you see this, Vita?
Yes.
So what you can see, there are two types of group, C double bond O. So if there is a C double bond O group, I'm going to get a peak here. And if there would be OH group, I'm going to get a peak in this region. I hope it's clear.
Yes.
Okay, now, perfect. Now let's go to the next one. Just a minute. So, all right. So next slide. Oh, I have to rub this. I'm so sorry. That's why I was not using it anyway. Yeah. So now, infrared spectrum of an ester. Now, just look at it and then think about it. That why this is showing a peak here. I'll give you 10 seconds to think about, and then we will discuss. Right? Yes, Anika.
Is it because of the C double O bond?
Yeah, because aster also contains C double bond O. So again, we are going to get a peak at 1750, around 1750. But you must have noticed that there is no peak in this region, that is OH region. This is very short peak, so we are not going to consider this. And you know that there is no OH bond in aster. Does it make sense?
Yes.
Good. Next. So next would be, here it is. What is it? One can tell the difference between alcohol, aldehydes, and carboxylic acids by comparison of their spectra. In case of alcohol, you can see a clear OH stretch, that is the yellow belt. Yeah. For aldehyde, there is a clear C double bond O stretch, the green belt.
Yeah.
For carboxylic acid, there are two stretches. I'm going to get, I'll look for two distinctive peaks. The first one should be at 1750, that is for the carbonyl C double bond O stretch, and another peak that is at around 32 to 33, 3600, that is for OH stretch. All right. So in carboxylic acid, we are going to have two stretches. In aldehyde, we will have only one stretch of the C double bond O. In alcohol, we will have only one stretch, that is for OH. Yes, Anika, is it clear?
Yes.
Ra, that's wonderful. Now, this would be given to you in the paper in the form of a data booklet. Yeah.
Yes.
So there is no need to memorize it. Everything will be given to you. Every data would be given to you. You simply need to identify that this peak corresponds to this group. So this is the, now have a look here. You can see that OH is in this region. If you have CH bond, it would be in this region. If you will have a nitrile, that is C triple bond N, that would be in this region, that is around 2200 frequency or wave number. If you have amine, then you are going to have around 3000 and 3200. If you are going to have OH, that would be from 3000 to 3600. If you will have a C double bond O, we have already discussed it. It's around 1750 to 1770. If we have a C double bond C, it would be from starting from 1590 and going to 1690. If you have aromatic carbon-carbon, then it would be around 1400 to 1500. If you have C single bond O, now Anika, have a look. If we have C double bond O, the frequency which will be absorbed is around 1750. If we have C single bond O, then the frequency which will be absorbed according to the stretch is 1100 till 1300. Can you see? Look, carbon same, carbon same. Oxygen same, oxygen same. The only difference is the bond. One is a single covalent bond and the other is a double covalent bond. So simply, if we simply look at the geometry of the molecule or the bonds being made, there is a lot of difference in the frequency which will be absorbed. Yeah.
Yes.
All right. Now going to the extreme right corner, CCl, it's going to give the the frequency which will be absorbed would be around 700 to 770. All right. And alkane has a very long rate CC bond of in alkane starting from 800 and ending at 1180. Is this clear?
Yes.
But you do not need to memorize it. I'm telling you again and again.
Okay.
All right. So again, this is another way. Maybe in your paper it would be given like this, or this, or this. So like this. This could be given in the paper, or this could be given in the paper. And you can easily see now what has been shown in it. Bond, class of compound, range, and then the intensity. Intensity is something which is not very much related to your syllabus, but still it's given. Actually, if the signal is strong, you are going to get a long downward peak. If the signal is weak, then you are not going to get a long downward peak. Maybe you'll get a broad and a small peak. Is it clear?
Yes.
All right, perfect. That's it. I hope it's all clear, right? So now I'll stop sharing the screen from my laptop and I'm going to start the uh, lecture on the iPad and I am going to share the screen with you as well. Okay. Now, I'll send you afterwards, right? Don't you worry about them. Only molecules which change their polarity as they vibrate. Now I'm going to leave from here. Just a minute. All right. So only molecules which change their polarity as they vibrate can absorb IR radiation. Example, water, carbon dioxide, methane, and NO. As I have already shown you the stretching and bending, so now I'm not going to go into the details, right? However, sorry. However, I have shown you the compounds downward. Can you see this? Like this is methane, yeah? So the stretching and bending has been shown, right?
Yes.
Okay. Molecules such as oxygen and nitrogen do not absorb IR radiation because there is no polarity. So if there is no polarity, there is no difference of electronegativity, then the infrared radiations would not be absorbed. All right.
Okay.
So this is a question in your past paper, that why oxygen and nitrogen do not absorb infrared radiation, because there is no difference of electronegativity, right? There is no polarity. You know that these are non-polar. You know that, Anika, yeah? Don't you?
Yes.
All right. Now, a carboxylic acid must have a peak for OH at this, a strong peak for C double bond O at this. I have already, because I have already shown you this, so I'm not going to go in a great detail. Yeah,
Yes.
this peak as well. Then comes a carboxylic. However, I will highlight these two things. A carboxylic acid. Then comes the other one, that is a carboxylic acid. A carboxylic, first we did a carboxylic acid must have, a carboxylic acid must have a peak at this and this. We did that. An alcohol must have a peak at a broad peak. This is the broad peak OH stretch. And then no peak at 1700. Can you see that? Can you see any peak at 1700? No. Look, no peak here. Why? Because there is no C double bond O in case
Okay.
of alcohol. It's ethanol. Can you see ethanol? Yeah. So
Yeah.
there is no C double bond O. If there is no C double bond O, you are not going to get any peak. I hope it's clear. Yeah.
Okay.
Do you want to ask any question, Anika?
No.
All right. A ketone. A ketone must have a strong peak for C double bond O. Ketone is this. Let me make this is ketone. Yeah. So what is the most important thing in ketone? This C double bond O. So definitely you are going to get a C. Can you see how long it is? How significant it is, right? So this
Yeah.
is C double bond O, and this is the fingerprinting region. And then this is a very small peak for CH, which is not very prominent, right? And
Yeah.
aldehyde mess. Now have a look here. I do want to keep both the slides on the screen. A ketone must have a strong peak at C double bond O, and an aldehyde must have a strong peak for C double bond O and weak peak for CH. All right. But why is this so? Why they have mentioned CH in this case, but they haven't mentioned CH in that case? Why? Can you think about it? Why?
I don't know.
No? What is present? If you make the formula of aldehyde, what would be more in it?
CH?
Yes, CH, which is not there in ketone, yeah? Because you know that when we talk about aldehyde, we must have one hydrogen atom present, yeah?
Okay.
So the one valency should be satisfied with hydrogen. Okay? So if I make it, are you getting it, Tanika? Yeah?
Yes.
All right. So if I will make it bitter, this would be like this for aldehyde. Have a look here. So this H. So I am going to say this CH. Okay. And this CH is not there in ketone. Look, it's CR. It's CR, right? So CH has been mentioned. Weak peaks for CH. All right. Now comes, now should we start doing the um, MCQs, if all is clear to you?
Sure.
All right. So the first MCQ is there on your screen. So what is it? Um, we have to, the picture which is given to us is this one, right? The infrared spectrum of one of these compounds is given below. Butane 1-ol, butane 2-ol, butanal, and butanol. And these are the bond stretches. Now have a look, and then which is shown here. Have a look. Okay. Just think about it, right? The infrared spectrum of one of these compounds is given below. This is ol, butane 1-ol, butane 2-ol, butanal, and one. So this is alcohol, this is alcohol, this is aldehyde, and this is ketone. So now tell me, what are you looking at is a very distinct peak at 1750. And this peak is for what? You know that.
The
This
aldehyde
is
or ketone.
this is for carbonyl group.
How?
Carbonyl. This is at 1750. I
But it's
told
the
you.
1740 to 1680 is an aldehyde or a ketone.
Yeah, I'm going to come to that point. The first of all, you need to say that it's for carbonyl. Now, carbonyl group is present in both the things, aldehyde and ketone.
Oh, okay.
All right. So first of all, you need to identify the group and then the classes. Okay. All right. So now that means that what you are going to get is for what? Most probably that we are going to have. I'm going to put a. Can you see any OH peak?
No.
No. So where should I put a cross? On butane 1-ol and butane 2-ol, should I put a cross?
Yes.
Yes, because there is no OH peak here. You know that the OH peak is around here. All right. So as we are not getting any peak, so that means it could not be A or B. So we are left with butanal and butanone. Now, the very first thing is no broad peak. I'm going to write no broad peak at 3750, from 3200 to 3750 for OH, so not an alcohol. Number one. Number two, strong C double bond O peak at 1700. So it is what? I have shown you the ketone as well. I'm showing you again. Here it is. A ketone and this. So what do you think? As is it a ketone or an aldehyde? Make a guess.
Aldehyde?
Well done. Because can you see that this matches with the aldehyde spectrum? Yeah. So it is aldehyde and not ketone. And it has why? It has weak peaks. If you remember, I showed you the weak peaks. Can you see these peaks? Yeah. Yes.
Yes.
And can you see these peaks? Is there any relation between these two peaks?
No.
No. Have a look, Anika. These peaks at the same frequency. Here,
They
check.
don't look the same.
Not. You know what? Actually, this is for the generic aldehyde. Here, I am giving you butanol. So butanol would be definitely different. This is a generic aldehyde. Anika, this is the generic aldehyde. An aldehyde should have a no. What are you not getting? I'll explain again.
No, I understand.
All right, fine. So has peak for CH of aldehyde has peak at 20, sorry, at 2900, 2820, and 2900, and from 2700 to 2775. So that means that it is not a ketone, it is an aldehyde. Have a look here. So this message matches with this. So 2900, can you see this part? This matches with this aldehyde. And this is ketone. Ketone is around 714 to 1714 to 1680, but this is for aldehyde and ketone. But this region, this is specific for this thing.
Yes,
Okay,
understand.
good. Now the next one. Consider the infrared spectrum shown below. Which of the following could have produced the above spectrum? An aldehyde, an alcohol, a carboxylic acid, or a ketone? Now, this is in front of you. Take your time. I'm going to explain it, but afterwards. First, you try to solve it on your own.
But I don't have the numbers.
You don't have the numbers. Okay, fine. If you don't have the numbers, can you identify this, which is at around 1750? And can you identify this, which is around 3200? Yes or no? Yeah.
But I don't know what those numbers represent.
Uh, this is for carbonyl and this is for OH.
But wouldn't I just
Now,
get the numbers in the exam?
you are going to get this. You are going to get these numbers. Here it is, with each and every question like this. But you know what? I don't have it here right now with me. It was on the laptop.
Okay.
All right. But you know what? What I'm trying to tell you is even if you don't have the number, you should memorize it that 1750 is a characteristic peak for carbonyl, and 3200 broad peak is characteristic of alcohol. So if you are going to add carbonyl peak plus alcohol peak, you are going to get carboxylic acid. Yes, Anika?
Yes.
I hope you are getting it.
Yes, I understand.
All right. So the combination of two is going to produce a carboxylic acid. All right. Okay. Next, this one. A sample of butanol was oxidized by heating under reflux with an oxidizing agent. If you are going to oxidize an alcohol, butanol, what you are going to get?
Um,
Butanol, have a look.
Tone?
Yep, right? So what you are going to get, because it's secondary alcohol, yes?
Yes.
So from secondary alcohol, we are going to get a ketone. So you can write here that we are going to get a ketone. Now make a structure of ketone. This is ketone if I'm not wrong. Yeah, this is ketone.
Mm-hmm.
All right, fine. So, and then the project was separated for infrared analysis. Apart from the peaks due to the CC and CH bonds, which peak would be present in the IR spectrum of the oxidation product? Now, can you answer me, please?
A.
A is what? All right, good. A peak due to carbonyl group only. What else? Any other hint?
No, I thought the answer was A.
All right, good. I hope it's clear to you.
It is A.
Yes, it's A,
Okay.
right?
Yeah.
Good, well done. Now the next one. Which of these molecules does not absorb infrared radiation?
C.
Oxygen, absolutely correct. Well done. What effects does, by the way, all these questions are from your past paper, right?
Mm-hmm.
All right. What effect does infrared radiation have on the covalent bonds in water molecule in the atmosphere? They are broken to form free radicals. They are broken into ions. The bonds vibrate more vigorously. There is no effect on the bond.
C.
C. Absolutely correct. Infrared spectroscopy can be used to distinguish between the functional groups such as alcohols and aldehydes. State how this analytical technique is used to do this and explain the effect of the radiation on the molecule. Specific values and experimental details are not required. So, state how this analytical technique is used to do this. Infrared spectroscopy can be used to distinguish between different functional groups, such as alcohol and aldehyde. So, if a molecule contains an alcoholic group or aldehydic group, so what is going to happen? Infrared would cause changes in the bond polarity. Yeah. Yes, Anika? Infrared would cause the change in the bond polarity, and different bonds would absorb different infrared radiations.
Yes.
All right. Because alcohol is this. Alcohol is this. And aldehyde is this. Yeah. So this is an aldehyde. So you can see that the bonds are different. So this is actually, this is the important bond and this is the important. These two are entirely different. So when the bonds would be different, don't you think that the strength of the bond would be different and they are going to absorb different infrared radiations? Yeah.
Hmm.
So may I write? So what would be the answer, Anika? That infrared would cause change in bond polarity. By the way, it carries 3 marks. Bond polarity. Number two, second, you will get 1 mark when you will write this. Different bonds. Which different bonds, Anika? This bond and this bond. Different bonds would absorb different infrared wavelength. The peaks obtained are then compared with the data booklet. Does it make sense?
Yes.
Any point which is not clear to you,
No.
please feel free to ask. All right. Next one. Give it a try yourself. Can you read the question, please?
It would detect whether the C double bond O is present because that would show that there's a ketone.
All right. So, if you want to know, you explain how infrared spectroscopy could be used to detect whether butane 2 has been oxidized. It's of 1 mark. So, 2 lines have been given in the first line. I'll write peak for C double bond O would appear. Yeah. And what about OH peak? What about this OH peak? Would it appear or not, or it would disappear?
No, it wouldn't appear.
All right, so it will be a peak for OH would disappear.
Do you need to
Yeah?
say that?
No, because this is interconnected to this question, which shows that you need to differentiate between two functional groups. So if you are sure that butane 2 has been oxidized, so the only product you are going to get a ketone, no alcohol.
So what I said was correct.
Yes.
Okay.
Yes, well, correct. It was correct, but it's better. I do want you to write the full answer. So you are going to get 1 mark when you will write this. All right. But I was simply telling you that there would be no peak for OH because it will get confirmed that butane 2 has been completely oxidized.
Hmm.
Yeah. There is no alcohol left. All right. Carbon dioxide and water vapor both contain polar bonds. What effect does infrared radiation have on the bonds in these molecules?
Stretches them.
And why stretch would be different? Because the polarity would be different.
Okay, so it stretches them based on their polarity.
Yes.
Okay.
All right. So you could write that as bond polarity changes, so they would stretch in a different way and would absorb infrared radiation at different frequency. Does it make sense?
Yes.
Well, prayer. This is a bit complex question. These three compounds, A, B, C, each have the same molecular formula, C4H10O, and are known to be alcohol. The infrared spectra of compound A, B, and C are shown. Identify one feature common to now. Identify one feature common to all three infrared spectra, which shows that A, B, C are all alcohols.
The peak at 3,400.
Excellent work. So you are going to get a peak So you will write broad peak. May I write broad peak? Should I highlight this? Yes, Anika?
Hmm.
I have highlighted it broad peak for OH at, you can write down, that is 3750 to 3200 centimeter minus 1. Now, state giving a reason for your answer if it is possible to identify each of these three alcohols on the basis of the infrared spectra alone.
Can you
Yes.
scroll up, please, so I can see the graphs?
Ah, okay. Actually, you know what, Anika? The examiner doesn't want you to concentrate on the spectrum given. He's simply asking a generic question that state giving a reason for your answer. If it is possible to to identify each of these three alcohols on the basis of the infrared spectra alone.
Yes,
That, how come? How come?
because
Haven't.
if they're alcohols, then the OH bond tells you that there's that it's an alcohol. There's no additional
But
P.
the question is saying, can you identify each of the three alcohols? Can you name them just by looking at the peak? Can you
Oh,
name
can I
them?
name them? No, I thought it meant if it was an alcohol.
No, 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 no. This question is written if it is possible to identify each of these three alcohols. Yes, Anika, what would be the answer?
No,
No, state giving a reason. No, this is stating and then now reasoning. What would be the reason?
it doesn't tell you how many carbon-carbon bonds there are.
Since all the alcohols, since all alcohols have the same type of bonds. Infrared spectra tells you that which bond would be there, but it is not able to identify the type of the alcohol. All right. So it can tell you, infrared can simply tell you alcohol is present. Whether it's butanol, butanol, propanol, methanol, it can't tell that. Is it clear?
Yes, but I don't understand the answer you wrote.
Why, Pite? What's the problem? I'll explain again.
Since all
No, since,
alcohols have the same type of bond,
yeah.
but
So which bond is there, Anika? Which bond is there?
OH,
OH bond. That's it. OH bond. Since all the alcohols are the same type of bond, that is OH. Look, so actually, this bond would be there in all the alcohols. So almost the same type of bond is there. Look, OH bond.
okay,
Look, just check this. Check this. Common, common, common. Yes? Now
yes,
this now check this part. This part. Common, common, common. So they are very close to each other. Although they are for three different compounds, but can't you see that they are all somewhat same? Yeah, Anika, look, they all are somewhat same.
yeah, I understand that.
Yeah. So by just by looking at the spectrum, you can't tell which type of, you can't name the alcohol. All right. Now this question: which pair of compounds can be easily distinguished by their infrared spectra? Can be easily. I'm going to highlight this. Oh dear. Easily. Can be easily distinguished by their infrared spectra outside the fingerprinting region. That means you are not going to consider the fingerprinting region. Can be easily distinguished. Distinguished means that they can be compared.
I I don't
So,
understand what they mean by outside the fingerprint region because I thought the whole graph was that.
actually, the thing is that this is the fingerprinting region, right? So
Just the
he,
right-hand side.
outside, that means you do not need to consider the fingerprinting region.
Is the fingerprinting region just the right-hand side?
Yes, yes.
Okay.
What the examiner is saying, that don't consider this, but is there any option which can be easily distinguished by their infrared spectra? Now have a look. What is this? C2H4.
Surely it would be COD because the alcohol isn't in the fingerprinting region. It's identified on the left hand side.
Yeah, but the thing is that, you know what, this one is alkene and this is alkane. This is butane, this is pentane. This is alcohol, this is normal alcohol, propan-1-ol, and this is propan-2-ol. This is what? Now, what is this? This is ketone, yeah? This is CH3C, sorry, this is ester, and this is also ester. Can you name them? So this is ethyl ethanoate, and this is methyl propanoate. Am I right?
Okay.
So have a look. Let me write. This is ethyl ethanoate. This is methyl propanoate. Now, please check, Anika. They are asking which pair of compounds can be easily distinguished. Now, have a look. The first one is alkene and alkane, two different classes. Now, let me write two different classes. That means one is having a double bond like this. This is C2H4.
I don't know where the different bonds are identified, so I can't answer the question.
No, look, have a look, just a minute. And then alkane. Have a look. Can you see that this contains a double bond and this contains a single bond? Yes.
Yeah.
However, come to option number two. Butane and pentane. Don't you think both are alkanes?
Yes.
So they are going to give a similar type of IR spectrum. Yeah. Now comes option C. Propan-1-ol and propan-2-ol. Both are alcohol. Don't you think they are going to give a very close IR spectrum because both of them are alcohols? And the last option. Both of them are going to give a very close IR because they both are esters. Now have a look, Anika. The first option, this is alkene, this is an alkane. Two different classes. So there would be a clear difference in the IR spectrum because one contains a C double bond C and the other will contain a C single bond C. So this is a very clear difference. However, there will not be a clear difference between pentane and butane because they both are alkanes. There would not be a clear difference in the IR spectrum of propan-1-ol and propan-2-ol because they both contain ol. There would not be a clear difference between ethyl ethanoate and methyl propanoate because they both contain ester group. So which one can be easily distinguished, alkane and alkene? What is bothering you, Anika?
No, I just didn't understand the question.
You didn't understand the question.
No.
All right. Actually, which pair of compounds can be easily distinguished? What
No,
is
I
the meaning
understand
of?
it now. No, I understand it now.
Okay. By their infrared spectrum outside the fingerprinting region. Even if you cut this line, still you are able to answer the question. Have a look, Peter. Still you can answer the question. Yeah?
Yeah, I understand now.
Yeah. This is a loop. This is a kind of a loop they have set for the student. So this is a pitfall, yeah? So don't consider this. If you are able to answer the question by considering the first line, it's all okay. Yeah. Now this question. The infrared spectrum, the infrared spectrum of a compound is shown. Use the information on page 5 and 6 of your. Now you need a data booklet for that. Can you do it as a homework?
Okay.
All right. And there are few questions more. They are not a lot. we have done till here. So if I give you this as a homework question, because you need to consider the information given on the data booklet pages 5 and 6. Describe how the infrared spectrum of propanol and electric acid will be similar and how they will differ. And these two questions. So can you do these questions as a homework question? It's
Okay.
entirely up to you. Whenever you want to submit it, when you feel easy, you can submit the homework. All right.
Okay. Okay.
All right. Any question, Bitter, the from the topic we have done? Because luckily we are able to start and finish the infrared spectroscopy in 1 hour. So we are done with the questions as well. So any
Okay.
question you want to ask?
No, I understand.
All right, that's perfect. Anika, would you please tell me about the topic you want to discuss in the next class so that I can prepare my notes?
Um, is this the end of topic, whatever topic this is, topic 7?
I think so. I think so. There were only two topics in this analytical technique chapter.
Um, okay. Is it okay if next lesson I just send you exam questions that I can't do by myself? It could be on
Sure,
any,
sure, sure. No problem, no
like,
problem. But,
the
but
not
yeah,
specific topic.
it's okay, no problem. But do send them in advance, right? So that I
Yes,
can
I
make a
will.
file.
Yes, I will.
All right, fine. Okay.
Thank you.
Okay. Well, thank you.
Thank you.
Bye-bye.
Bye.
Bye.